Great, thank you.
Hey, so I'm pretty new to this group. I just found out about you guys, and I was just wondering, like, any tips for me to catch up with you guys?
Yeah, so what we've done so far is we've gone we've gone through the first 4 notebooks
Okay.
in the class, and we've gotten through all of the sort of the classical, um, the portion of the class that deals with the classical natural language processing up to deep learning. And today we'll start the deep learning part. So I would say it's not impossible to catch up. I think we'll probably be at it until May. If you look at the schedule,
Yeah, I know I've
there's
seen the
this,
schedule. Yeah.
yeah, and so yeah, I don't think it's too late to catch up if you have the time to. And you know, I've been reworking the notebooks to make them more accessible and maybe correcting some of the small errors and so on. So you should
Okay.
probably um, clone the Git repo that I've made for the study group, which I have a link to in that. You're on the Slack group, right?
I'm not. I was wondering if you could give me access to that.
Oh yeah. So I'll put that information. Let's see. Let's see. I'll put that information on the on either the chat. Probably late after the meeting. I'll do it. I'll put it. Let's see. No, I need to put it on so you can get it. I'll put it on the chat from
Okay.
this Zoom session.
Um, so do I need to have like an email address that starts with or has the words TWIL or something in it?
No, that won't be necessary. That's
Okay.
not necessary.
Okay.
Let me see if I can get the chat. Yeah, because usually I should. How did you find out about this? Did you find out about it through the FastAI forum?
Yes.
Okay. Um, let's see. I believe did you the
I just
thread that,
posted the Joseph. I just posted the link
Oh, okay.
where someone can join. It actually mentions about Fast AI, but I think anyone can join using that particular link.
for the Slack group, you mean?
Yes.
Thank you so much. That's great. Okay. Yeah. Also, the Shafali, the posting on the FastAI forum also has a link to where you can join TWiML, because it has the calendar, it has the link to TWiML and everything else you need. So yeah, go to the TWiML link that Manis Snesan just put up and join TWiML, and then you'll be granted access to the Slack group.
Okay, great. I'm gonna do that right now.
Yeah.
Thank you.
Okay. Are there any questions before we get started with this one? Maybe I'll wait a little bit more for a few more people to show up.
Hi, this
Maybe
is
more.
Darren. This is Darren. Thanks for updating the notebook for
Oh
my.
yeah. How did that work out for you?
Oh, I just looked at it this morning. There's a lot happening under the hood in the Fast AI, but I can see where it's happening.
Great.
I
That was my
don't quite
intention.
understand. I mean, I don't understand what's happening, but at least
Yeah.
I can see. That really
That's
helps.
okay. That's okay. Yeah, I must say, I had a epic battle with that notebook, because it kept it kept making all kinds of excuses to fail. I mean, and I had to fix a lot of things, and it's not. I'm not blaming the FastAI people. I think that my problem is that I have a Windows 10 machine, and mostly the FastAI people are working in fact, I know they're all working in Linux. And there are just some things that work on Linux in FastAI that don't work on Windows, and nobody knows. I mean, there's
Yeah,
a lot of.
I've mentioned it before, but it's really worth considering is using my whole dev environment on my Windows 10 is Docker, so I do everything in Linux.
Yeah, I'm going to have to. I think I'm going to have to switch when we get to the FastAI. When we get to the next class, where they go into the version 2 library, I think that's definitely broke. As far as I know, it's definitely not working for Windows 10. So I'm going to have to make the switch then. It's just that I have a dual boot machine, and it's just too much of a pain to have to boot into Linux with all my stuff.
Dude, do not forget about that world. That's like old world. I mean, it may be a little, it would be nice if you have someone who can help you, but I did it all on my own. But, you know, I'm a little bit more of a developer, but, you know, because Windows now finally with Windows 10, you get Docker Desktop. It's like built to do it for Docker. So you can do it. And then
but there's
once you've used Docker, there's no going back, buddy. No. Yeah.
But there's a problem with Docker, though. The problem with Docker is you cannot access your GPUs.
Well, if that's the case, I did not. I mean, I haven't even used a GPU, so that could be a critical flaw. Yeah.
Yeah, that's. I would have done it otherwise a long time ago, but.
Yeah, you said that before. I forgot about that.
Okay, let's get started. Yeah, so here we've actually finished the classical part of natural language processing, at least as much as Rachel wanted to do, and now we're moving into using deep learning for natural language processing. So in this notebook, we're going to see how to construct a language model for IMDb, which, remember, that's the International Movie Database. We're going to construct a language model for IMDb, but with a twist. We're going to use transfer learning to do it. And this is something that was pioneered by Jeremy and one of his students. I forget the name of the fellow now.
Sebastian.
Yeah, Sebastian. Yeah.
Ruder.
Sebastian Ruder, right?
Yes.
Yes. And Sebastian's, for his PhD thesis last year, he invented a way to do transfer learning for natural language processing, which was a huge breakthrough. And what we're going to see today is that we're going to crush the state of the art from 2017 with the work that we're going to do today. We'll see how with transfer learning we can crush the world, the natural language processing world, the way it was in 2017 before Sebastian's thesis. So it was a huge breakthrough. It's like it's the same as the same order of magnitude as the breakthrough in 2012 when they applied that famous computer vision data set. They learned how to use transfer learning to go from the image data. I think it's called what's it called? ImageNet, the giant million image data set. And then once you solved ImageNet, you could then make transfer learning. You could then use transfer learning to make successful models that work on smaller, more specialized image data sets. And that's what's going on with natural language processing. Now we have this huge Wikitext 103 database, which has millions of words from Wikipedia, and then we make a language model based on that data set, and then we can apply it to smaller, more specialized language data sets like movie reviews. So that's what's going on here. We're going to do two things. First, we're going to use transfer learning to build a language model. And what is a language model? A language model, at least in words, is very simple. It is a model that if you give it a phrase, a few words, it will predict what the next word or two words or how many words you want should be. So for example, you could give it all of Shakespeare's work as the input and build a language model based on Shakespeare, and then you give it a phrase you give it a phrase, and then it will complete the phrase in a way that Shakespeare might have done. That's the kind of thing. So basically, a language model predicts. You give it a sequence, and it predicts what's next in the sequence. And language models are very general. They don't necessarily just have to be words. They can be characters. You could give it a sequence of characters, and then it could predict what's the next character could be. You could give it a series of musical notes, and then it could predict, if you've built the language model out of a jazz database, for example, you could give it a few musical notes, and then it will predict what a good next musical phrase would be. So they're very interesting, language models are, and it's a more general example of what we would call sequence modeling. That is, sequences of objects in time. and then you give it a sequence, and it will predict the next items in the sequence. So, and then the second part of the lesson, we're going to, instead of with the language model, we're going to build a sentiment classifier for the IMDb database. That is, you give it a movie review, and it will tell you whether that review is likely to be a positive review or a negative review. We've seen this already when we use naive Bayes, but now we're going to use deep learning to do the same task. And well, the result is going to just crush what we got with naive Bayes. And even remember, our best result was not with naive Bayes, it was with logistic regression. I think we got something like 88% or 89%. We'll see that with this, with deep learning, we're going to get almost 95%.
Hi, Joseph.
So, yes.
I'm just wondering, how can one achieve this language model in low resource languages where we don't really have enough data resources? So can we use transfer learning for the language model itself to another language?
You know, I haven't looked into that too much, but that's a really fascinating question. And I think a bunch of people from FastAI have looked into that. And there's an appendix, the last item in our notebook today talks about that. But in general, I'll just say a few general things. A language model basically encodes the structure of the language in terms of its grammar and so on. And because languages have a lot in common, you know, for example, the word for man and the word for woman will have like a similar encoding in different languages, you know, because it's used in similar ways, like, you know, like women have children and men go to war and these kind of things. So any language model is going to encode some kind of a relationship between men and women, and let's say human beings and animals, and let's say metal and rock. I mean, these things are all going to be encoded in the language, and it'll be similar for all different languages, or you know, so that's why if you can get an English language model working, you can leverage that to get a language model for other languages. And I think that's what's happening. They're building language models for all kinds of languages now. But refer to the appendix at the end of the notebook for more on that. I think FastAI has a whole, there's a whole group of people in FastAI that's busily involved in doing just that, making language models for other languages.
Okay, cool.
Yeah. Any other questions before we get started? Okay, so so the first thing we do is now the first section of this notebook is, I don't know why they did it, this section 1, because all they do is they download the sample, they talk about tokenization and numericalization, which we've already done. Oh, maybe the whole thing is to illustrate the data block API for loading in the notebooks, but I think we've done that too. So I think you could even, in fact, if I revise this notebook, I think I'll just delete section 1 because it really doesn't do anything that we're interested in. Section 2 is where we get started. And the first thing we do is we get the full IMDb data set. That's what this line does. And then, well, I can execute. Some of these I can execute because they don't take that long, but some of them take hours. So if you want to run this notebook, probably the best thing to do would be to turn it loose and let it run overnight. Unless you have a really powerful GPU, in which case it'll run faster. But it took me, I think it takes maybe 20 hours or something for me to run this thing. Okay. They talked a little bit about the Wikitext 103 data set and how you can use it to pre-train a language model. Let's see, 100 million tokens extracted from the set of verified good and featured articles on Wikipedia. and you can download it. Let's see, 2 times. We use Wikitext 103, so we don't use this Wikitext 2, which is much bigger. Let's see. Okay, so the very first thing we do is we download Wikitext 103. This takes a little while to do. When you've done it, you want to unzip it into the FastAI. When you set up FastAI, you will have in your home directory, you'll have a subdirectory called .fastai, and in that subdirectory there will be a bunch of folders that FastAI uses. One of the folders is data, one of the folders is images, and one of the folders is models. And those are the places where FastAI knows that the data, the models, and the images are stored. There's some kind of a config file that FastAI has that tells it where this is. So the first thing you do is you unzip it into this special folder, and then it'll be accessible. The next thing we do is we pre-process the IMDb data, and we package it up into a data bunch so that it's ready to use for modeling. So this thing I had to do this workaround. I think you've seen it before because we've downloaded this data set before. And I wrote this little simple wrapper that basically, what happens is I get a broken process pool error. But I found out that the broken process pool, and the broken process pool error happens almost whenever I try to use this use FastAI's text API. And this is only for Windows 10 that this happens, as far as I know. So I found a workaround because the broken process pool error turns out to be stochastic. That is, it doesn't happen every time. It only happens sometimes. So I take advantage of that, and I wrote this little wrapper that just keeps trying. It's a try-catch block. It just keeps trying it until it works. And then it tells me how many times it took to work, to get it to work. So I'm not going to do this because sometimes it takes a bit of time to get it to work. It fails a few times, and then it works. Okay, once you've got that, we can look at, we've got the data bunch is in data_LM. So now we can look at its vocabulary and its training data set and so on. We can look at how long they are. I think I've got them loaded up so I can do this. Nope, I don't have them loaded up yet. Well, I'm just going to go on. Okay, so the first thing you do when you get this done, because it takes a while to do, is you save it. You save it right here. And then we can load it. So then if you come in again, you've already done this step and you don't have to do it all over again. And we'll see that we're going to use that strategy throughout these notebooks. Whenever you go through a long process where it takes a long time to get some processing done, you save that intermediate step so that you can then come in and load it up again when you need it instead of having to go through and generate it all over again. It just makes a lot of sense. Okay, so so now that we've loaded the data, we've loaded the, let's be clear on what we did. We loaded the Wikitext 103 data set, we pre-processed it and made it into a data bunch. And that's what this data LM is. It's the Wikitext 103. So, I'm sorry, let me back up. That's not the Wikitext 103, that's the IMDb data. So you have to keep in mind the two different things going on here. There's the IMDb data, which is the specialized set of data that has just movie reviews in it. And then there's the Wikitext 103, which is this huge database that has something like 100 million tokens in it from the Wikipedia articles. Okay, so we're going to be using both of these things, but we want to be clear on how we're using them. So the first thing we did was we loaded in the IMDb data, packaged it up into a data bunch. That's what this part does. And then this is the transfer learning step. Okay,
I have a question, just
sir.
why do we not specifying label for a language model? I see that it was commented out.
That's a very good question, and I kind of glossed over that, but I'm glad you asked me that so that I can go back. When you do this and package things up into a data bunch, there's a step in here where we label for a language model. That's, I broke this up into 2 steps. So originally I tried to do it all at once, but then I decided to break this part off. So that's what I'm doing in the second piece.
Okay, never mind. Got it.
Yeah. So
All
now
good.
we're labeling. Right, but your question is still good because this is a step where we label it for a language model, and labeling for a language model is different than labeling it for a
For the classification tasks.
Yes, for the classification. Because with a language model, we don't really need labels. The words themselves are their own labels. When we try to predict the next word, we already know what the next word is in most of our data set. You know, we have, if you pick some phrase from Wikipedia, you already know what the next words are. So those are your labels. And so that's why it has this special, the FastAI API has this special method called label for language model, and it knows that. So that's going into the under the hood. FastAI has a very slick API for pre-processing data, and this is one of the methods you can label for language model. Later on, we'll see that we do a different method at this stage when we want to build the classifier. Okay, continuing on, I wanted to highlight the transfer learning step because some people went through this notebook and they got very confused about where the transfer learning was happening, and that's because it wasn't actually made clear. So one of the things I did when I reworked this notebook is I tried to make clear what we're doing at each step. So this is the step where the transfer learning happens. We're gonna build a language model learner with the input data bunch, data LM, and with the model from AWD LSTM. And this object here has the pre-trained weights in it, the pre-trained weights from the Wikitext model. So this is where the transfer learning happens. We're importing into our language model learner. We're telling it, use these as the pre-trained weights. So it's not starting from nothing. It's using the pre-trained weights that we got, that somebody got when they built the Wikitext 103 language model. And that step, we're not going to do. That's a step that has to be done with a huge amount of processing power. It takes a lot of compute to do that. But we're benefiting from that. We're getting the pre-trained weights in this file here, and we get to use them. So this is what happens under the hood. Somebody built this Wikitext 103 model, Stephen Merity, and he stored away the weights so that we can all use them and benefit from them. So this is where the transfer learning is happening. We're transferring the information that we got, that Stephen Merity got out of his Wikitext 103 model, applied to 100 million tokens from the Wikitext 103 database. And we're importing those weights in this file. So this is the magic. This is where the magic happens right here.
I have a question.
Yes, sir.
Is that a recurrent neural network, the AWD LSTM?
It is a, that's a really good question. This is an LSTM. So it's the next, it's sort of an improvement on an RNN.
Okay.
Yeah. And so this, the field of natural language processing has been moving really rapidly in the last few years. And, you know, RNNs and LSTMs used to be the state of the art just a few years ago. Now, all of a sudden, LSTMs are not state of the art. It's attention models and this thing called BERT that was developed by, I think, by Google. And we're going to be learning about that later on in this class, but one step at a time. We're now where people were in, let's say, 2018. This was state of the art.
See, let me ask you a question. The language model learner, that I guess object from the FastAI API, is that used solely for transfer learning?
That is,
or is it more, it's the general language model learner thing?
It's a general one, but it has in the machinery to be able to do transfer learning because it accepts pre-trained weights in this input here.
Yep, I'm with you. Great.
Yeah. So I suppose if you if you didn't have pre-trained weights, you might leave this part blank or something.
Okay.
Yeah, of course, it would be interesting to run it with it and without it, right?
Yeah, it would. And it'd be interesting to see the comparison of the results you'd get.
Joseph,
wanna
are you
try that?
sure that AWD LSTM is the weight, or I thought that was the architecture of the model?
That, you
Yeah,
know what?
the way it's described, that's what it seemed like. That's one other reason I was confused.
Yeah,
Yeah.
the architecture with the weight.
It might have both. It might have the architecture and the weights.
Yeah, it probably has to, because somehow it has to transform the IMDb stuff into that architecture. Because
Yeah, and this all depends on us using the same model for our, for our neural net as Stephen Merity used when he built the Wikitext 103 model. Otherwise, the pre-trained weights wouldn't make any sense, because the pre-trained weights have to, they refer to some architecture.
So
right?
also, I'm looking at the language model learner API right now and documentation, and it has pre-trained as an argument that it's defaulted to true. So in general, when you do this language model learner, you probably use some kind of pre-trained model.
Yeah, and so if you wanted to run it without, without pre-trained weights, you could just set that to false, and then you wouldn't have to import any weights. So, yeah, so this is worth looking into. I think it was a good question. Does AWDS, does this just specify an architecture, or does it also include the weights? I'm thinking that it has to include the weights, because otherwise, where would they come from?
Yeah, that is correct. It includes the weights.
Mm-hmm. But it's a good point. It's the weights. I incorrectly said that this is only the weights, and someone corrected me and said that no, it has to have the architecture too, and that's correct. Okay, so now we can look at
So how this AWD LSTM is now get connected to Wiki 103?
AWD LSTM is the model, is the actual neural network model. It specifies the architecture of the model that was used in Wikitext 103, and we're going to use the same architecture in our model. That's what this line is.
But it has not just the architecture; it has the frozen weights. That's
correct.
That's the frozen weights from training a huge language model.
Correct. That's the key point. So this has both the model and it has both the architecture and the weights of the model that was used on Wikitext 103.
And that's the step you have above where you specifically say download the Wikitext 103.
Yeah, we will when you download that, it stuffs it in your data, in your .fastai/data directory, and then that's where it becomes available to use in this program, in this And if you should try this notebook, I think it should work. If anybody has any trouble with it, please let me know and I'll fix it and find out what was wrong. What I think is this notebook should run as is. But if you have any trouble, because it runs on my machine, but if anybody has any trouble trying to run it, just please drop me a note and I'll look into it and fix it and make sure that it runs. Okay, so once we have the once we have the language model, we can now have the vocabulary. We can look at it. This is just this is just to check that we have the vocabulary. Now we take out the model in we call it AWD. And then remember, this is it's a model with the pre-trained weights, but we haven't done any training ourselves yet. So this is an untrained model. You can get the model itself, and you can also get the language model encoder out of it. So
I'm sorry, when you say untrained model, so you've got the wiki trained model, but you have the IMDb model is untrained. We just have the vocab for IMDb right now.
Yeah, it's pre-trained. It has the pre-trained weights from Wikitext 103, but we haven't
adjusted it.
We haven't fine-tuned it.
Joseph, maybe the better word is untuned model, because it is pre-trained, so it's trained, but it's not
I like that.
fine-tuned to IMDb.
It's pre-trained, so it's trained, but it's untuned. So the
But
fine-tuning needs to be done.
what I'm wondering is the vocab at this point. Is this just IMDb vocab, or is this Wiki and IMDb vocab, or is it just Wiki vocab? I'm confused.
Let's see. That's a good question. I think it's the IMDb.
Yeah.
vocab.
Yeah, I don't think we have access to the Wiki vocab through this data bunch, because this data bunch has the pre-trained model from Wiki, which are just weights, right, and an architecture, but I don't think it has the vocab in there.
That's right. It has the data that came into it is from the IMDb. That's this data, the data bunch from IMDb. So it only has the IMDb vocab in it. So let's see.
Okay.
Yeah, because that's what we're doing here. Data LM. This is not the model. This is the data bunch, right? This is the IMDb data bunch that we just built.
Yep.
That's its vocabulary. Okay. So now they do things. They break the model down into its model part and into its encoder part. So just for, I mean, if you have this thing, you have everything. If you have the learnlm.model, that's everything. But you can also break off the piece that just corresponds to the encoder. And the reason for doing that, I suppose, is that it's much smaller than the whole model. So I don't, it would be nice to run this line, but I don't have this, I haven't actually executed this step yet, because this is the time-consuming step. So I haven't executed it yet, so I don't have access to this, to data LM yet, because I haven't actually built it. I mean, I did it when I ran through the notebook, I built it, but today it's fresh, so I didn't build it yet. So don't think this is that this is an error in the notebook. It's just because I haven't executed the parts that lead up to this. This is not, there's nothing wrong with the notebook. It's just that I hadn't built the data underscore LM yet. So that's why I can't run these lines to show you, but it would be interesting to see this, to see how big the encoder is, and to know that it's much smaller. The encoder part is much smaller than the whole model. Okay, now here's where we do get the Wikipedia text, and we can compare them. Let's see, this thing here, ITOS underscore weight 103 has in it the vocabulary for wiki text. And so when we load that, and then we can start comparing, it has the vocabulary and its string to index and its index to string parts. So Wiki ITOS, once we load it in, then we're going to be able to compare it. That's the vocabulary for Wikipedia, and we can compare it to our IMDb vocabulary. Maybe it would be better to, instead of call this vocab, we should call it IMDb vocab, so that there won't be any confusion here.
Yep.
But yeah. So then they go through a few exercises to show, just playing with it, looking at it, seeing which words are in one vocabulary and not in another one. They're not the same. The Wikitext 103 vocabulary is, as you expect, much larger than the IMDb vocabulary. And you might also think that IMDb vocabulary is going to contain specialized terms. It's going to be mostly specialized things that would occur when you talk about movie reviews. So you're going to be talking about action and blood and love and romance and stuff. These things that are, and horror, all these things that are specialized to movies and not necessarily occurring the same in Wikipedia. So there might even be some terms in IMDb that don't occur in Wikitext 103. Okay.
Can I ask a question, Joseph?
Yes, sir.
So we do not know how the tokens were created for the Wikipedia language model, right? So I mean, we would assume that like this is a simple word tokenizer, but what if this was typically like not specified in the pre-trained models, right? Do you follow my question?
Yes, that's a very good point, because there are a lot of different ways to tokenize. So we've seen how we've built simple tokenizers in the last couple of lessons. We used the count vectorizer, and we actually built our own tokenizer in the last lesson. We can only hope that when they built the tokens for Wikitext 103, they used a similar process. But you're right. I mean, there are a lot of different tokenizers like Spacey and Sentence Piece, different kinds of tokenizers that are in wide use. So that's a very good question to raise.
Yeah, depending upon that situation, we might end up in where our domain tokens will be much larger, and we have to completely rely on this language model that we are going to train in order to get the weights for these out of vocabulary words or tokens.
Yeah, that's a good point. So if you could look that up and see, what they did, what Stephen Merity did for his tokenizer, that would be interesting to see if he did something similar to what we did.
Yep.
But right now we'll just assume that they built the tokenizer in a similar way. Let me take a pause and look at the chat and see what's going on in the chat. Let's see. Okay, so somebody's asking about, let's see. I'm just looking to see if there's any questions that I want to answer. A bunch. Okay, I think people are doing a good job of answering each other's questions here, so that's good. Yeah, drop mult. Okay, so somebody asked a question about drop mult, and somebody else answered it well. So Srinivas answered it well. So drop mult is specifying how dropout is to be used in these in the LSTM. If you've taken the FastAI version 1 class, you've come across this concept of dropout, where you randomly drop nodes in a layer of the neural network, and it helps to regularize and helps you to get something that's more generalizable. So as I recall, the dropout parameter that I saw was 0.3 in that line where we built the model. Let me see, that's up here. Sorry, it's up here. Yeah, this drop mult is specifying a hyperparameter that tells you what fraction of nodes to drop at random, and that's taken as 30% here. So yeah, okay, so that's the chat. Okay, continuing
and
on.
that just makes the model more robust, right?
That's correct. It makes it more well. We say it makes it more regularized. When you drop out nodes, you're sort of crippling, in a way, you're crippling a little bit the network's ability to fit itself to the data. You're giving it less flexibility to fit to the data. And if you do too much of that, you're going to cripple the model too much, and it won't be able to fit your data. But if you do it just a little bit, 30%, then it cripples it just enough so that it doesn't overfit to the data.
Yep, it's an anti-overfitting neural network device.
So the net effect is that it's more generalizable. When it sees new data, it can do a better job of fitting it.
Just a point of clarification. In this particular instance, drop mult actually is, as you said, a hyperparameter where it's not directly just used as a single 30% 0.3 value, but it actually is a ratio or a number that then FastAI uses to set about 5 different dropout parameters that the AWD LSTM model actually uses. So this single 0.3 number is translated into a variety of about, if I recall correctly, 5 different dropout values that AWD LSTM actually requires.
That's really interesting, Srinivas. I wasn't aware of that. Can you say a little bit about what these 5 parameters are, if you remember?
If you look at actually the AWD LSTM paper, I mean, it uses dropout like left and right. I mean, there are like 5 or 6 different levels or layers at which it uses dropout. I don't, off the top of my head, recall all the different dropout numbers or layers where it uses them, but because it is a fairly complicated multi-layer LSTM model, it actually uses regular and Dropout, as you were mentioning and discussing, is essentially used for regularization. And because this model is so heavily parameterized, it regularizes heavily. And by that, I mean it uses a lot of dropout. And so if you go and read the paper, and I don't recall because I read it a while back, it uses, if I recall correctly, again, it may be 6, it may be 4, but it uses a multitude of actual dropout values. And in order to simplify usage, what FastAI and Jeremy did is just abstracted it to a single parameter which you supply, which he has kind of played with to figure out what the good value of parameter is. And then that's the parameter that's drop mult. And based on that drop mult, about 4 or 5 different parameters, dropout parameters for the AWD LSTM model gets set to different values.
Got it. Okay, so
that's very helpful, Srinivas. Thank you.
Yeah, thank you. And I say, so would you say that these parameters are, since there are many layers in the LSTM, would you say that the dropout is maybe being varied at different layers, so that
Yes.
it's heavily used at one level and much more lightly used at another level? So
yes.
Yeah. Okay. So you might start with 0.3 and then say, okay, for the first couple of layers, 0.3 divided by 2, and for the last couple of layers, 0.3 times 3. 0.3 times 1.5 or something like that.
Yeah, it's some
actually,
some internal formula. And if you read if you read the paper and also kind of watch the relevant lecture in FastAI, not the NLP one, because he doesn't. He might even get into it, but definitely the original FastAI version 3 lecture set 1. Then he
can I
gets
interrupt?
into it.
Excuse me. So I went ahead and looked in the ULM fit lecture, and Jeremy actually mentions what the drop mult does. Jeremy has fixed some default parameters for the drop mult values for each dropout values for each layer. And when we apply a drop mult value, it effectively multiplies the dropout values with drop mult. So for example, for a hidden layer, the probability of dropout is 0.5. So when we use the drop mult of 0.3, it will multiply it with 0.5, and the effective dropout for that layer will be like 0.15, something like that.
Yeah.
Okay, so it's using 0.3 as a base parameter, and then it computes the actual dropout for each layer according to whatever their prescription is. So some layers might get a higher dropout value, some layers might get a lower dropout value, but they're all mostly 0.3.
So as we increase the drop mult, the regularization increases. That's the general idea.
Right. Okay. Yeah, thank you so much for that. I did not appreciate that that subtlety, and thank you for bringing that to our attention. Okay, so here we are at this training step. Now we're going to, or I should really call this something like we already have pre-trained weights, but we want to fine-tune maybe. So maybe this should be called the fine-tuning step, because as Srinivas points out, the model is already trained on with the Wikitext 103 weights. Now we're going to specialize to IMDb, and we're going to train it with we're going to fine-tune the training to specialize with the data that we have, which is the the IMDb data in this data bunch, right? So let's see. So we first specify a batch size. I think we did that up above, way up at the start. A batch size, I guess Rachel has a lot of processing power at her disposal because she had batch size of 192. I knew that wasn't going to work on my machine, so I started with batch size of 48, and that did work with for the language modeling part. I was able to get it done. Let's see, where are we here? Here's the training set. Okay, so I chose a batch size of 48. Then they set this hyperparameter LR, which is the learning rate. And they also put the model on FP16. If you have a processor that can do that, that can do mixed precision, that would work. I do have a processor, a GPU that can do that, so this part worked for me. It might not work on your GPU. If not, just omit this part. I should make a note about this. Let's see. So I'd recommend that if you don't have mixed precision option, because mixed precision will go faster. Okay, and then I found that it took me an hour and 42 minutes to train. I have an NVIDIA RTX 2070 GPU. I have a local machine that does it. If you're working on Colab, you have more power than I do. You have more processing power than I do, so it'll be faster.
How much do you have any idea how much a GPU like that costs? Can you buy it? You have to get it installed when you get the computer.
Well, okay, I have it in my laptop. I bought a laptop with it, and the laptop cost about $2,000. Now it's cheaper. So I bought this laptop maybe 9 months ago. So it's much cheaper now, and there's more, and it's not state of the art anymore either. So I think there's other versions of the even the 2070 that are better than the one I have. Anyway, so train the model. Complete the fine tuning. We then unfreeze and launch a new training. So what does that mean? That means, okay, what are we doing here? We are, we're just training the last layer when we do this. It basically unlocks the last layer and doesn't use the weights from LSTM and from the AWD model. It doesn't use the pre-trained weights for the last layer on this step. So it basically just trains that last layer. Then it takes a long time to do that. So again, we save the result.
Question. I'm sorry. What do you mean trains the last layer? I mean the wiki already has a last layer. So you're are you using the IMDb data?
It throws the pre-trained weight, the last layer of pre-trained weights away. It throws them away and solves them itself. It uses all the weights up to that layer, freezes them in place, but it unfreezes.
But I don't understand why. I mean, it's not using the IMDb data, so why is it
It is using the IMDb data. This LearnML, this learner is based on the IMDb data. It has the, but it's importing the pre-trained weights from the Wikitext model in it, right? But the data.
Okay, then it's basically doing, transfer learning, which is retraining that last layer, the output layer.
Exactly right. It's doing the transfer learning there.
Excuse me, Joseph.
It's undoing the transfer learning. It's undoing that last layer and training it. Well, no, sorry. You're right. It's transfer learning. It's training the last layer specifically on our IMDb data. Okay. Well, somebody else has a question.
So, what is the purpose of doing this mixed precision?
Oh, it's just for speed. In other words, instead of using 32-bit numbers, you use in 32-bit floating point numbers, you use 16-bit numbers, and it's faster. It's less precise too, and that is actually a regularization step. When you mess up the precision of the numbers, it has the same effect as sort of messing with the model and crippling it a little bit, like I was saying. You can't get as precise a result, and therefore you can't fit to the data. You can't overfit to the data as well. So it's a regularizing step too, as well as faster. Does that make sense?
I mean, the question would be mixed precision as opposed to what other kind of precision?
Oh, full precision. You could
where you have a lot more decimal places. That's full precision.
Yes, exactly. Instead of 32 bits, 32 bits is full precision. 16 bits is half precision. And if you do things in half precision, you can do not only faster, but you can do twice as much. You can have bigger batch sizes.
Yep. Without hurting your model at all, probably.
Without hurting, well, you hurt it a little bit. It's not as precise, but that is actually a regularizing effect. So just remember, if you don't have the mixed precision available, you just don't do this piece. Okay. All right. So we fit one cycle. Only fitting
one other detail there, Joseph, is the FastAI model specifically is coded to support FP16 because the reason why that's important is it's not just a simple matter of porting everything to FP16. There are steps in the process that need to be done at the 32-bit or full precision. And that's true of certain additions and multiplications that happen during, I believe, backpropagation or other steps. And FP16 can be used in some steps and not in other steps. And FastAI takes care of that level of detail. So you just need to be aware that you just can't do to FP16 on anything that you're working on. You can do it if you use FastAI because it takes care of the detail that I just mentioned. That is, some steps can use FP16 and some steps in the process cannot.
Yes, I remember that, and I don't remember which steps. They have it explained in one of the FastAI lessons how this 2FP16 process works. Because as you say, some of the steps you actually need the full precision and other steps you don't. So that's why they call it mixed precision. And you're right, it's not just a simple thing, and FastAI takes care of it all of those intermediate steps under the hood. And so it looks very simple, but it's not, as you say. All right, so after we fit the last layer, now we unfreeze it and let it try to refit all of the weights from the bottom up. And this also takes a long time, and I was able to complete it with a batch size of 48 again, and I didn't run out of memory. And then when we finish that, we save it and we call it the fine tune model.
So it's, I'm sorry. So again, it's kind of like the first step there was priming the final layer without really using the wiki weights. You're just priming the final layer probably on the IMDb data, and then you're doing the whole thing.
Yeah, so we're priming the last layer, but remember we're using all of the Wikipedia weights except the last layer, and we're solving the last layer of weights. We're solving it specifically for IMDb data, but we're accepting all of the pre-trained weights from all the pre-trained weights of the previous layers from the wiki text model. Does that make sense? And we're just training the last layer on specifically for IMDb.
No, I know, but you're doing it in two. I understand that fully, but you're doing it in these two steps.
Yes.
And the first, I'm trying to understand the difference between the first and the second step. I'm saying the way I'm guessing at it is the first step seems like it's just training that final layer using the IMDb data, and that's it. And then the second step, and it's just sort of using that as like priming that final layer. And then the second step is it's training using all of the wiki layers.
Yes.
No, but it's important again to listen to what Joseph said, which is even in the first step, you continue to use for everything except the last layers, the weights from the wiki test. So it's not just the last two layers. You still keep the weights of the previous layers.
I know you keep them, but in the first step, you're not using them.
Yes, you're not allowing them to be tuned by what you're doing.
Change is the right term. So the Wikipedia weights are not changed, but except for the last layer. Like
that's correct.
Yeah, and the reason
but it's, the Wikipedia numbers are not changed in both of those steps. So once you're done, the first step and the second step.
No, I think you got it the first time you said it. The first time they do this, they just train the last layer, and then when they've done that priming step, as you say, then they say, okay, now turn it loose and let it resolve for all of the Wikipedia weights. But we're not throwing them away. We're using those as the initial values, and then we're seeing if we can improve on them. So we're not actually throwing away the Wikipedia weights. We're using them as our starting point, and then see if we could and I think that's true for the first step too, where we only solve for the last layer, we're actually using the Wikipedia weights as our initial value, but then we free it up to say, start with the Wikipedia weights, but see if you can get a better result for this particular data set.
So step one, you do use the Wikipedia weights.
Yes.
You don't change them, but you use them with the IMDb data to train
Yes.
the output layer. Second step, you're letting the whole language model adjust itself to the IMDb data.
But starting with the IMDb weights. So
Excellent.
it's not
Yeah,
like
no, I get it. But the IMDb weights are weights actually that are coming from the IMDb data run through the unchanged wiki model to the final layer.
Let me back up. I think you have it, but let me just make sure. So the first step where it says, okay, let's freeze all of the wiki text weights, the wiki text 103 weights, except for the last layer. And let's use the last layer, let's use the wiki text weights in the last layer as a starting point, but then let's let the model solve for better values that apply for the IMDb data set.
Yeah, this is great. I appreciate it. This really shows how it works. That makes perfect sense to me.
And I'm not sure why. And then the next step where they say, okay, now using the wiki text weights as starting points, see if you can get better values that apply to our IMDb data set. And I'm not sure why they do it in those two steps, why they don't just do the whole thing all at once. If anybody else understands that, you can feel free to jump in. But I'm thinking that Jeremy and company found that this two-step process worked better for them.
Conceptually, think of it even as what you would do. Set aside the language model for a minute and think of what you would do in a conventional or convolutional neural network trained on images. So what happens in that case, if you have read the papers where they analyze it, is a lot of the beginning and intermediate layers are used actually by the network to learn. The very first layers learn very basic vertical line, horizontal line. And then as you go deeper into the network, it learns to put together what it has learned previously and kind of compose more complex objects. And along the way, the final layers help to tune all of that and classify into what the images are on the output. So in general, conceptually, as you go deeper into the network, the final layers are working to fine tune or to tune the network learning and point towards the classes or categorization classes that you are predicting, which is the reason, even if you go back and look at convolutional and what you do in images, you strip out the last two layers, and you attach the last two layers which you want to predict the number of classes that you actually have.
Yeah,
so for example,
I see that in a classifier that, like, if you have weights pre-trained from ImageNet, there were 1,000 classes, but now you want to classify dog breeds and you only have 10 different classes that you're interested in. So obviously the last layer has to be restructured to look for 10 classes instead of 1,000 classes. So that would make sense. But in this problem, it's a language model. So there's no difference between the last layer, what the last layer in this model is trying to accomplish, and what the last layer, there's no difference in what the last layer of IMDb is trying to accomplish and what the last layer of Wikitext is trying to accomplish.
Yes and no. The vocab that ultimately it's again predicting. In a language model, it's just predicting the next words. Yes. So in that sense, it's just utilizing or fine-tuning the next word prediction to the type of words that it sees in IMDb rather than what it has seen in.
Yes, that's a good point, because if you gave Wikitext a movie review and asked it to predict the next words, it would not do the same thing as if you wouldn't expect it to do the same thing as if you gave the IMDb model a movie review. The IMDb model is specialized to understand the structure of movie reviews, and so it would have a different answer.
Exactly. So it helps train the final few layers or layer to what movie review language is commonly, or what is common in movie review language corpus as opposed to the wiki text corpus.
Yes. So it's learning, as you say, the different layers are learning something about the structure of how the language gets used. And language in wiki text is you can imagine that its structure is a little different than in movie reviews. Movie reviews are likely to be people just bullshitting about what they think about movies, and they're using slang, and some of their words aren't even words. You know, they're not. You've seen on these on the internet where people don't spell the words right, and they don't use good grammar and all that. That's a completely different kind of language usage than in wiki text, where people are trying to be precise. You won't find so many grammatical errors because people correct them. So it's a completely different it's a completely different kind of language usage, and that's what you're trying to do when you're pre-training. You're saying, okay, let's start with the structure that we learned from wiki text, but now let's specialize and learn the new structure, the new ways of using language that we find in movie reviews.
That's right. It's fine-tuning it to the movie review corpus. And much like you would, and you can hear Jeremy say it in the lectures, if you were to use it for medical corpus, then you would again fine-tune it on that. If you were to use for legal documents, then you would fine-tune it on that. So the base backbone is similar to what you would use in visual models like ResNet or Inception. And that's the language model here of AWD LSTM. And then you fine tune it to the language corpus that you want to use it on.
That's really well put. So yeah, so we should be aware of that this is what's going on in the field today. Is you're taking a big general purpose language model like Wikitext, and now there are even bigger ones with billions of tokens in them. But then you use that to specialize training to smaller sets, and as Srinivas points out, some of the main applications are medical. So you could look at medical records processing, and doctors speak in a different language almost than normal people do. So there's a different structure to medical patient records than you would find in Wikipedia. And the other big application is legal, and there are other applications as well. You could even talk about news articles and science papers and things like that, and books could be another subspecialty. So yeah, it's a really exciting field. You use a big general purpose language model to try to learn a smaller specialized language model, and that's what we've done here. So at the end, we finish after we unfreeze, we train. We're done. We save it because it takes a long time. Then we've got a language model. And what can you do with a language model? You can generate fake movie reviews. So
I have a question.
I guess they try some. I don't have any examples because I haven't run the notebook at this point, so I don't have. But here's what they do: is they feed it what they think is an initial phrase from a movie review. And then they give it the number of words that they want it to generate and the number of sentences that they want it to generate. And then they use this lm.predict method. And it tells it, okay, generate 40 more words in 2 sentences that follow this phrase. And there's this temperature hyperparameter that I haven't looked into too much, but if anybody knows what that means, I think it maybe adds some randomness.
It says how much to depend on either previously learned words or something of that nature. So it's kind of, like you said, a level of randomness, and how much to depend, how much to use random versus previously provided words, or something along that dimension.
Right, and so when you run this notebook, and in fact the saved notebook that Rachel has the examples in it. My notebook might also, because I might have run it before I saved it, before I committed it to the repo, or maybe not. I should actually run this thing from start to finish and then commit it to the repo so that you can see the examples. I think I'll do that in the next few days. But anyway.
Sorry, there was a question from Charles, I believe. Go ahead, Charles. just before that, Joseph, there was some question.
Yeah, I did. It's about the fit one cycle. I sort of remember Jeremy saying something like if you do more than one epoch in the fit one cycle, you end up overfitting the final layer. Is that correct? Is that why you should only be doing fit one cycle only with one epoch?
That's a good question, because he did only fit one cycle. He did only fit one cycle in this part, but then in the next part, when he does the classifier,
after you unfreeze it, then you do more than one epoch. So I'm just wondering if you should always be doing just one fit one cycle with one epoch, or
no. That's not the case, Charles.
Okay. Heard that? I'm not sure.
No, you can do many more epochs. In general, it's just a matter of the fit one cycle just says it uses one cycle for the parameter and varies it in how it varies it within a cycle. It increases the learning rate and then drops it on a cosine basis. But you can absolutely use more epochs, both in training these kind of models as well as in training convolutional models. So fit one cycle doesn't mean you have to just use a single epoch.
So this is before unfreezing, you can do more than one epochs?
Sorry, would you repeat?
Before you unfreeze it, you can do more than one epoch on fit one cycle?
You can. Whether you want to is a different question than whether you can. You can absolutely, you can do it.
You'll be doing that. That's the question, sorry.
Yeah, I mean, what you do is you want to look for the loss function, and when the loss function, when the training loss function is always going to keep going down, but the validation loss function will eventually start to go back up, and that's when you see the validation loss function start to increase. That's when you know that you've overshot, okay, and you don't want to train anymore. And we'll see that actually. If you run this notebook, you'll see that happening in the classifier. I know I saw that happening in the classifier. But
yes, so anyway, just to answer specifically, looking at the notebook now. So the reason Jeremy just trains with one cycle is without unfreezing. And when you unfreeze, then as Joseph explained, you are actually fitting a different last layer or layers to the model and then training. So you're fine tuning when you do that. Before fine tuning, you are actually having the entire model, and that is the pre-trained model. So you don't really want to retrain that entire model on your IMDb data set. So because you don't want all of the weights to be changing based on the IMDb. Those weights for most of the model are already very well tuned to the Wikitext data set, and you want them to stay that way. That's why you just kind of run it for 1, 2, a very small number of cycles. You unfreeze. By that, you get rid of the last layer, put in a new layer, and then you train much more to fine tune it to the IMDb data set. That's why Jeremy does it this way for this particular notebook.
Okay, great. Thank you.
Thank you. Okay, so at the end, you'll see examples, although I don't have them here, but when you run the notebook down to here, then you can actually see the kind of movie reviews that it produces. Then they have a section on misuses and risks of language models. I think I'll leave you to read that. One guy, I guess some people from FastAI built a language model based on based on Stack Exchange. They took all this text from Stack Exchange posts and they built a language model that could that could talk in that language. And then as a joke, they made that. And so people could ask questions that you would normally ask Stack Overflow, and then you'll get these phony answers because the language models aren't really that good yet. You'll see that when you solve this, I don't have the numbers here, but because I haven't run it, I have actually run it, but it was lost. I have to run it again. But when you look at the results, you'll see that the accuracy is only about 40%. In other words, predicting the next words only works, it doesn't work that well. But it's certainly good enough give phony reviews that sound reasonable. And it also is good enough, as we'll see, to build a really good classifier, state-of-the-art classifier. But anyway, so these language models that we're building aren't that great as far as language models go. So you can imagine that when somebody tries to build a Stack Exchange language model, it's going to give some really phony and misleading answers. And people did that as a joke. And you can imagine that if they tried to put this on Stack Overflow, there would be a lot of very mad software engineers because it's gonna lead them on a merry chase. Anyway, so that's this Ask RoboFlow, and the point is that Ask RoboFlow is not yet ready to really answer people's programming questions. But as language models get better, you might be able to build something like that you could ask it a general question about software engineering, and you could get a really good answer. And that's probably going to happen in the near future. Anyway.
So is the recent Mina chatbot by Google a language model, or it's some specialist chatbot?
Yes, yeah. It's more than that too, because it can answer questions, and it can access data and so on. A chatbot has to do two things. It has to keep the conversation going. It has to be responsive to what you tell it. It can't just be repeating things, and it has to have it has to say interesting things. So if you ask it how are you feeling good today, and it says yes, I'm feeling good today, that's not a very interesting answer. It has to do something more interesting. So apparently this Mina chatbot is really scoring high on all the tests that they would use to evaluate whether a chatbot is good. And it can, I think long ago we reached the point where a chatbot can pass the Turing test. They can actually say things, it can carry on a conversation and you won't know that it's a chatbot. You'll actually think you're talking to a real person. Anyway, so the last section is where we take our language model and then we use it, we take our language model and we use it to build a sentiment classifier. And we're now going to have to load and pre-process the data all over again. But this time we're going to, I had to decrease the batch size from 48 to 24 to get it to work. It took a long time to fail, but it ended up failing with memory CUDA out of memory error. So I had to try. I took it down to the batch size of 24, and then I think, let's see, I think that eventually that I had to go down to 8 to get it to work. So yeah, so this is the same process before. I had to use this brute force method to get around the stochastic error from the data bunch, from the data from FastAI's text API. Doesn't work well on Windows. But this brute force method, at least it works. Sometimes you have to wait a long time for it to work though. But notice the difference here is we're going to label things differently. We're going to label it from folder classes, the negative or positive classifications. So that's the different thing we're doing here. We didn't have to do that when we were building a pure language model. Here we're building a classifier, so we're going to label the data as we saw, as the training data has negative and positive classes. Okay, so we did the same. So the rest of it's the same. You form a data bunch, and then once you've done it, you save it because it took a long time to produce it. And then this is what the batch looks like. These are the movie reviews in their tokenized form. And now we're going to create a language. We're going to create a model that just a classifier model. We load the encoder that we had from before, that part of the model that we're going to need. And then we build this text classifier learner, given the data bunch, and again, the pre-trained weights and this architecture of the Wikitext 103 model. And we're using the same multiplier. I'm not sure why she Rachel did this. She took off the 2FP16. Maybe she had trouble with it or got better results without it or something like that. So that, I didn't do this. This is part of the original notebook. She took off the mixed precision part. Okay. So here again, we're going to go through this unfreezing. We're going to go through this freezing and unfreezing process. So first we freeze the weights. We look for what a good learning rate would be. Then we train for 1 cycle. And then we unfreeze the last, don't ask me why they're doing this. This is probably something that fast AI people experimented with and found the right recipe. So you unfreeze the last 2 layers, train for 1 cycle, unfreeze the last 3 layers, train for 1 cycle, and then finally unfreeze all the layers and train for 2 cycles. And here I got this very weird CUDA error, but when I tried it again, it worked. So again, this is a stochastic error. I looked this up, and it's a known problem with PyTorch when using an LSTM, and I found this is the reference to it. But fortunately, it doesn't happen all the time. So when I tried it again, it worked. Before I even tried it again, I want to note that we already beat, I don't have the intermediate result above, but we already had beaten the 2017 pre-transfer learning state of the art, which was, I think, 91%, no, 94.1, that's what Rachel said. So here, our final result is 94.8%. So we not only beat this model, we beat it by a lot, the 2017 state of the art. So here I do have some results from the end. I have a movie review that, I give it a text from a movie review. That's what the classifier does. You give it the text of a movie review, and then it predicts the result, whether that would be a positive or negative movie review. So you just make up a fake movie review. I really love that movie. It was awesome. And then you ask it to classify, and it's very sure. The output is the probability of these 2 numbers, by the way, are the probability of the negative class and the probability of the positive class. And you can see that it's absolutely positive that this is a good review. So it knows, it looks at that text and it says, yep, that's a good review. And then you give it a fake bad review. I didn't really love that movie, and I didn't think it was awesome. And it's not confused at all. It knows that that's a negative review. So it's not bad. You can do more tests on it too. This is just an initial test to see if it does what you think it should do, and it does.
So Jeremy, this is Darren. So I guess I'm theoretically behind this. I'm not sure I understand. So basically, you've added an extra layer on top of the other layers at the end for classification. So you're basically using it's one big model, which has all the stuff we did before to adjust the language model, and then to that same model, you're adding another layer for classification. Is that what's fundamentally happening here?
Yeah, we had to tack on a layer for classification, yes.
Okay. So when I've seen transfer learning used before, that makes sense to me. But when I've seen it used before, basically you can just use the vector space from the language model. You just get a vector out of it, and you can almost feed that into any classification model. So, but I understand this is a different.
Yeah, the last layer of this neural network has to be a classification. It's going to give you up or down, and so you have to do that to make it into a classifier.
Basically, the decoder is changed in case of the classifier. In language model, the decoder is used to predict the next word, while in text classifier, it predicts the class.
Oh, so the decoder layer, is that the last layer? No, that's different. That's different because
that's a group of layer. The encoder, what we do is we save the encoder weights in case of the language model, and we use it with the text classifier.
Right. So we weren't doing anything with the decoder layer up till this, like at all. It didn't even.
For the text classifier, no, but in language model, we did train the decoder layer because we had to fine tune the previous layers as well.
Did the wiki layer come? So the wiki language model came, even before we adjusted it, came with the decoder.
Yes.
Yeah, yeah.
And we saved it. We saved it, and there was a step above where we saved it, and we called it fine-tuned encoder, fine-tuned end. And here's where we pick it up and tack it on to.
Right. So basically, when we were saying we were training that last layer, that's the layer that predicts the language, the next word.
Yeah, in our language model, yeah. But in this one, the last layer is the part that predicts the up or down.
Oh, no. Now that fully explains. I'm like, why the hell are we readjusting the model again to our data? Well, it's because we have a completely different prediction layer, right?
Yeah, the classifier solves a different problem than the language model does.
Yeah.
And then someone asked about, so I think we're done, but the last part, someone asked about different languages, and this is where they talk about it. I just called it the appendix, but it says FastAI alumni have applied ULM fit to dozens of languages and have beat the state of the art in Thai, Polish, German, Indonesian, Hindi, and Malay. So there's a very active community in FastAI working on these less well-known languages. Well, not less well-known, but I mean just less popular than English. Probably Hindi is more used than English because there's more people. So, yeah. So there's a lot of activity in this area. And ULM fit refers to, I think, I'm not sure exactly, it refers to Sebastian Reuter's paper. That's what they called the model. And I think what we did in this notebook is the same thing. It's almost the same as ULM fit by doing the fine tuning from Wikitext 103 and applying it to a smaller, and using transfer learning to apply it to a smaller database. So I actually got us there 8 minutes early. We have time for some chat or some questions if anybody wants to.
So I have some questions about this. So to talk about the pre-processing of when you want to typically, like the general the state of the art is like you typically start with a pre-trained model, right? So what types of pre-processing that you would typically like look out for, or like maybe if we start with just a simple toy data set, like in this case IMDb movie reviews, and we know that it's mostly like words, but in case of Twitter, there'll be a lot of emojis and then like URLs sharing. And I just wanted to know like what types of pre-processing you would do. And
that's a good question. I hadn't thought about that for something more like a Twitter, like a Twitter database, let's say. I mean, as a first cut, you could probably try to process it exactly the same way as we did the IMDb data.
Yep, that's what I did. But I just wanted to know, like, there are like few other things that you would do as well, right? So
yeah,
depending upon the task.
Yeah, I mean, you might add tags for URLs maybe, so that for example, just like we saw in our tokenizing step, there's a special token that says capitalize. This word is capital. The next word is capitalized. They invented a special token that says that. You probably could invent another token that says the next word is a URL.
Mm-hmm.
You know, that's one thing you do. Or the next word is an emoji. You know, the next token is an emoji. You could invent new tokens like that.
Basically, provide a token attribute and then like give an indication to that language model.
Yeah.
Okay.
And then it would know. It would have more. It would maybe handle those things better because it would understand more about the language, because it wouldn't say, okay, our new language has not only words, but it has emojis and it has URLs in it.
Okay. As a follow-up, you actually showed this this out of vocabulary, right? Where these are the words that are not present in the Wikipedia vocab, and you showed some form of an intersection or a difference. I don't know what it is.
Yeah, they went through it. Yeah, that's right.
Actually, like when before we actually fine-tune it, if we actually like save that encoder that is on the first step itself, would that actually like provide an idea about these are the out of vocabulary words that are specific to IMDb? And I'm just trying to think in terms of pre-processing, like that would give some ideas.
No, that's a really good question, because I think I glossed over that step. There is a step where they look for the words that aren't in
Yes. Yes.
that aren't in IMDb, and they set those words to be random or something like that. Let's go back and find that step. I think I remember there was a word, a keyword.
Yes, that's the part that I was really looking forward to.
Let me find that part.
Yes, the IMDb not in Wiki, or is that the one?
All words that appear in IMDb but not in Wikitext 103 will be initialized to the same random vector in the model. As the model trains, we will learn their weights. Okay, so let's see what that means. So here's the, before we think about that a little bit more, here's what they're doing. One of the things they're doing is they're saying, okay, look in the IMDb vocabulary for the word modernization, and then it, because you got, and then it will find that word. And then you can say, is that word in WikiWords? And then it will answer that. I don't have the answers because, as I said, I have a fresh version of the notebook and I haven't run it yet, but I have run the notebook, but this particular version is a fresh version. So I don't have the answers to these questions. But so it's basically going through the exercise of finding some words that are in IMDb, but not in Wikitext 103, and words that are in Wikitext 103, but not IMDb. So, but this is the sentence that speaks to the question that you had. All words that appear in IMDb but not in Wikitext will be initialized to the same random vector in a model. So that happens automatically. And then as the model trains, it learns their weights. So that makes some sense. Except I would have thought the other way around. I would have thought you're interested in the words that appear in Wikitext, but not in, no, I guess you don't care about words that appear in Wikitext, but not in IMDb. You only care about the words, you only care about the words that are in IMDb, but not in Wikitext. So Wikitext doesn't have all the answers because the specialized vocabulary might have, the specialized movie review language might have words that don't appear in Wikitext 103. So, and I think that Rachel found a few here, and that's the next few lines here. So what do you do about that? Those words, you initialize them to random vectors and let the network learn the weights. Does that make sense?
Yeah. So once you save that encoder, you will have those. You will have a representation of those words, which is what get used in the classification task.
Yes.
So yeah, it's in a way that like discourages the pre-processing part of it, right? Why would you want to pre-process if language model takes care of this, right?
No, the language model, remember one thing, that the mapping is originally done all of the unknown to random, and then as you fine tune, those words will move. They'll not all stay at that. The
That's right. That is,
helps
I understand.
move.
I understand that part. But where will you make the trade-off between, okay, let me make sure that this difference between those vocabulary, right? I'll let me process my IMDb tokens, as close as possible to the Wikipedia, so that I make use of the pre-trained weights rather than train it for my downstream. Like that's the part. Like I don't know where to make those trade-offs. How much of pre-processing should I do it, to match the vocabulary as close as to my pre-trained vocab. Does that make sense, or am I confusing?
Yeah, no, that is true. But remember that at least in these instances, in most of these applications, you're bound by even, overall, for example, in this case, they only use 60,000 word vocab
that
for
is
even
correct.
wiki text.
Yep.
So the upper bound in that sense is 60,000 because that's the bound of the wiki text vocab to begin with. Right. So,
yes.
I mean, now the final answer to where you're headed is to say you train your AWD LSTM itself on the IMDb data set, because that is a way of eliminating your question completely.
Exactly. Yep.
Okay. Because you don't even have the problem because there is no two vocab. There's just one vocab on the thing you want to tune it on.
Yep.
So now to your question of how far to go down, it's not, frankly, from what little I have seen, it's not as much. Now for a Twitter thing question you asked, it's very relevant, but for IMDb, it is not, because the difference of trying to match between 0 and 60,000 to really enable your score to go higher is not that fruitful. You see what I'm saying?
Yeah. So the thing was, it's actually like happens when in case of where your downstream tasks contain more punctuations, and where these punctuations actually like mean something. For example, error messages and code related stuff.
Correct. And if it's so different from what the AWD LSTM is actually trained on, then it's better to train the model on your data directly.
Yep.
So for example, for Twitter, I would probably train the after some pre-processing to, as Joseph mentioned, of, saying the next is URL, the next is emoji, because that allows the model to know when is an emoji likely to appear, at the end, at the beginning, at the middle, after you say some specific word, blah, blah, blah. So you would train the fundamental AWD LSTM model on Twitter data, and then apply it to variations of Twitter, subsets of, Twitter classification of movies, subset, if you will. But the base training would have to be with those punctuations included versus on Wikitext. So as your final task data varies dramatically from what you're trained on, it's better to train it on that itself. If your final data is somewhat close to Wikitext, then you don't need to go through, and that's what transfer learning helps you with.
Okay, so that's where my trade-off. Okay, thanks, Srinivas. Yeah. So.
Thank you, everyone. I think we just went over by 3 minutes, but I think it was worthwhile to have that discussion. So I'll just check out and end the meeting, and I'll see you all next week. Thank you all.
Thanks, Joseph.
Thanks, Joseph.
Okay, bye.
See you all later.
Yeah.
See you. Thanks, Joseph.